Okay, guys, week 4. I'm going to include this guy in your notes for this week, although I know you guys already have that somewhere in your notes. I gave that to you previously. But just in case you misplaced it, because this guy comes in handy with some of the things we're looking at this week. I will also include this guy as well. Once again, I know you guys have this, but just in case anybody misplaced it, you know, this guy always comes in handy. Okay, I wanted to definitely bring in this. Okay, these power reducing formulas, these guys are not on here, okay, but they are basically a derivation of these half angle identities. We're going to need these guys here. Okay, so I can show you how we come up with these. I'll just show you one of them because they're all real similar. So we'll just do this top one. So if you go to this half angle identity, okay, right here, okay, which you guys, you know, have, and we have this sine of theta over 2 equals plus or minus the square root of 1 minus cosine theta over 2. Okay, so if we take that guy right there, okay, and you notice that if you square both sides, okay, you're going to get sine squared of theta over 2 equals 1 minus cosine of theta over 2. And then notice if you say, you know, I don't like this half angle, so let's just let x equal theta over 2. Then if I multiply both sides by 2, I get 2x equals theta. And then notice we can substitute this guy in here and substitute this guy in here, and we get sine squared of x equals 1 minus cosine of 2x all over 2. Okay, so that's all it is. All of these guys are just derivations, okay, of these half angle identities that we really haven't done much with, I think, since last year in pre-calc, but this comes into play this week when we're working on these problems with trigonometric substitution. Okay, now these guys, a lot of times you will see these guys written a little bit differently. Okay, a lot of times you'll see these in books, they'll write it as 1/2 times the quantity of 1 minus cosine of 2x. I use that a lot as well. And this guy, same thing, they'll write that as 1/2 times the quantity of 1 plus cosine of 2x. Okay, I have a tendency to use these guys here rather than use these guys, but it doesn't really make any difference. It's just a matter of what you want to do. Okay, let's see. Okay, trigonometric substitution. Okay, I also have this in your notes for this week. Okay, so if we're integrating functions that are in one of these three forms, okay, where you have a square root of constant minus x squared, square root of a constant plus x squared, or square root of x squared minus a constant, many times we can do this using trigonometric substitution. Okay, and this trigonometric substitution is all based upon these two Pythagorean identities, okay, which obviously we know that guy off the top of our head. This guy, we see it on a regular basis, so you guys are familiar with these. Okay, so I'm not worried about that. All right, now how do we do this? Okay. All right, so, and again, this is in your notes. Okay, if we have an integrand that contains this square root of some constant minus x squared, okay, we can write that constant as the square of some number a, okay? And so we would always substitute in for x a times the sine of theta. And so notice that a obviously would be the square root of that constant. Okay, if we have the square root of a constant plus x squared, okay, we would substitute in a tangent of theta, where once again a is the square root of that constant. And then if we have the square root of x squared minus a squared, we would substitute in a times the secant of theta, where once again a is the square root of that constant. Okay, now you say, well, you know, why does this stuff work? Okay, I'll show you. Okay, one of the biggest problems here is getting rid of that square root. Okay, that's what makes our life tough. Okay, so, you know, why does this work? Okay, so if we look at this first one right here, okay, it's a squared minus x squared. So I go here and I say, okay, that's right here, so I have to put in a sine of theta for x. Okay, so for this guy, we would say, okay, x equals a times the sine of theta. Okay, and so I get the square root of a squared minus a sine of theta squared. Okay, so we look underneath and we say, okay, well, notice you're going to have a factor of a squared here and a factor of a squared there. You can pull that out. So that's a squared times a quantity of, I would have 1 minus sine squared of theta. Well, going to our Pythagorean identities, we know that 1 minus sine squared is cosine squared. So we're going to get the square root of a squared cosine squared theta, and obviously that's a perfect square, and when you take the square root, you get a cosine of theta. Okay, and so what happens is it gets rid of that radical, and that's one of the problems here. Okay, so we say, okay, well, what are we going to do on this guy? Okay, you go right back to this sheet I gave you. Okay, and so we say, okay, x equals what? Okay, that's right here. Okay, so we put an a tangent of theta. Okay. All right, so let's see. We would get the square root of a squared plus a tangent theta squared. Okay, once again, notice that we have a common factor of a squared, so if I pull that out, I'd be left with 1 plus, I would have tangent squared theta. Right there. Okay, and then we go to our Pythagorean identities. 1 plus tangent squared, right here is secant squared, so we substitute in secant squared. And again, notice that you have a perfect square, so we can take the square root and we get a secant of theta. Okay, so once again, just like the first one, it gives us the ability to get rid of that square root. Okay, then we go to this last one, x equals, okay, so I go here and we say, okay, what are we going to put in? It's like this. Okay, so we're going to put a secant of theta in there. And notice how I keep going back and referring to this. That's why I gave it to you, make your life easier. Okay, so we put that in there. And so I'm going to get the square root of a secant theta squared minus a squared. And again, you have a common factor of a squared. So we pull that out. And I'd be left with secant squared theta minus 1. And then we go to our Pythagorean identities. And we say secant squared theta minus 1. Well, that's going to be tangent squared theta. Okay, right from there. Okay, so we get the square root of a squared tangent squared theta, and of course that's a perfect square, so we take square root, we get a tangent of theta. Okay, so that's why all this stuff works out. Okay, So obviously that's why I wanted to make sure you had all this stuff in your notes, okay, rather than trying to copy it down from a video. Okay, but keep going back to that stuff. Okay, it's all important, and we will get through one of these today, and then we'll take up with some other ones tomorrow. Okay, so we have something like this. Okay, and it's kind of a cool problem and cool process. It is a little bit on the front end and a whole bunch on the back end. There's a whole bunch of stuff we got to do on the back end. Okay, so it's going to take up some room. There's no doubt about that. Okay, so we're looking at this guy. Okay, and I'm thinking, all right, that would be the same as square root of 2 squared minus x squared dx. Okay, and then I go here. I say, okay, it's just like this top one. Okay, so notice that my a here would be 2. And so I'm going to have to substitute in a sine of theta, so that's going to be 2 sine of theta. Okay, so let's see. My x equals 2 sine of theta. All right, so that goes in here, but I've got to deal with the dx. Okay, so just like u substitution, we say, okay, let's take the derivative of both sides. Okay, so dx, and 2 is just a constant multiplier. Okay, the derivative of the sine of theta would be cosine of theta. And now your dx becomes d theta, because theta, okay, is your variable of integration. Okay, so now we're going to take this, substitute it in. Okay, so let's see. I get square root of 2 squared minus, okay, x is 2 sine of theta, 2 sine of theta squared, times the dx now is 2 cosine theta d theta. So 2 cosine theta d theta. Okay. So let's see what we got going on here. Okay, notice I have a constant multiplier of 2 squared. Okay, so I pull that away. 2 squared times the quantity of, I'd have 1 minus sine squared theta times this 2 cosine theta d theta. Okay. All right, now notice my radicand here is a perfect square, okay, because that would be 2 squared times, using your Pythagorean identity, cosine squared theta times our 2 cosine theta d theta. Okay, so taking the square root here, I get the integral of 2 cosine theta times 2 cosine theta d theta. All right, so notice I have a constant multiplier, 2 times 2. So that's just 4. I'm just going to put that guy out front. So we had 4 times the integral of cosine squared of theta d theta. Okay. All right, so you go to that first sheet I gave you, and we say, okay, I need the integral of cosine squared. Well, we go here, and we don't have that there, okay? We've got cosine, okay? And obviously we have secant squared and cosecant squared, but we don't have cosine squared. Okay, so we say, okay, how are we gonna deal with this guy? Well, this is where it comes down to our power reducing formula. Okay, so these guys right here. Okay, I want to get that cosine squared theta down to cosine theta. So if I use this second one right here, notice it takes cosine squared down to cosine. Okay, so if I use this guy right here and substitute that in there. Okay, so let's see, I'm going to get 4 times the integral of, I would have 1/2 times the quantity of 1 plus cosine of 2 theta d theta. Okay. So far, so good. Okay, so let's see. We can take that 1/2 out front as a constant multiplier and multiply it by the 4. Okay, so we're going to get 2 times the integral of 1 plus cosine of 2 theta d theta. And then I have to integrate those one at a time. Okay, so you could do that in your head. You could do it in your head, or you could actually write it on a paper. So let's see, that would be 2 times the integral of 1 d theta plus 2 times the integral of cosine 2 theta d theta. Okay. All right, so we get to this point right here, and this would be like 2 times the integral of dx. So we know we're just going to get x. So in this case, rather than x, you get theta. Okay, so this guy right here is just 2 times theta plus, but this guy right here, it's not cosine theta, it's cosine of 2 theta. So I've got to use u substitution here. Okay, so let's see, if I let u be 2 theta, then my du is 2 d theta, but I want it to be d theta, so I get 1/2 du equals equals d theta. Okay, so we go use this back in here, so I got the 2 out front. Okay, this would be cosine of u times 1/2 du. Okay, so let's see, I've got a constant multiplier here, 2 times 1/2, so that's just 1. So I've got this 2 theta plus the 2 times 1/2 is 1, the integral of cosine of u, so that just gives me the sine of u plus c, so it'd be the sine of 2 theta. Okay. All right, so we're close to being done, but not all the way done. And here's the problem from here on out, is notice that I'm starting with something where x is my variable, so I have to end up with something where x is my variable. Okay, so let's see, we're going to bring this guy, we're going to go up here and say, okay, how do I come up with something for theta? Okay, well, let's go all the way back up here. Okay, so if I can isolate theta, okay, I'm sorry, I gotta move that down, go all the way back up here. So if I can isolate theta there, we're in good shape. Okay, so let's see, if I take that guy, I say, okay, well, if x equals 2 sine theta, then x over 2 is sine of theta. And notice I could take sine inverse of both sides to figure out what theta is. And remember, sine inverse is the same as arc sine. So I could say, okay, this would mean that theta is the arc sine of x over 2. Okay, so that takes care of this first part of it. Okay, all right, so let's see. I'm going to get this 2 theta, okay, becomes 2 times arc sine of x over 2. Plus, okay, now I'm still running into some problems here because that's sine of 2 theta. Okay, I would rather it was sine of theta, but it's not. Okay, it's sine of 2 theta. So we say, okay, how am I going to deal with that? Okay, so if we go back here to our double angle identities, sine of 2 theta is 2 sine theta cosine theta. Okay, well, why not make that substitution? Okay, so I'm going to substitute for sine of 2 theta. I'm going to substitute in 2 sine theta cosine theta. Okay, so let's see. This guy becomes plus 2 sine theta cosine theta, and our plus c. Okay. All right, so let's see, what can we do there? All right. Well, I know this part of it's done. 2 arc sine of x over 2. Okay, plus, let's see, 2 sine theta. Well, if we go right back up here, isn't sine theta just x over 2 right here. Okay, so why not substitute in x over 2 right there? Okay, now cosine theta. This is where you have to use your Pythagorean identities. Okay, so going back here, where's my guy at? Okay, which this is one where you know off the top of your head, I need cosine of theta. So why not subtract sine theta from both sides and then take the square root? Okay, so let's see. So cosine theta would be square root of 1 minus sine squared theta, plus that's c. Okay, and I'm going to bring another piece of paper in here. Okay, so we've got this whole thing we have to deal with. And let me bring it over here. Okay, so we have 2 arcsine of x over 2 plus 2 times x over 2 times the square root of 1 minus sine squared theta plus my constant of integration. Okay, so we got rid of the theta here. We got rid of the theta here. Now I got to get rid of the theta here. Well, we already know that sine of theta is x over 2, so why not put x over 2 in there? Okay. Let's see, we have 2 arcsine of x over 2 plus, notice when I go 2 times x over 2, I just get x, times the square root of 1 minus, and sine theta is just x over 2, so that's just x over 2 squared plus a constant of integration. And notice how we got rid of all the thetas. Okay, so now it's just a matter of just cleaning this guy up. That's all I'd do. Okay, so let's see. We've got 2 arcsine of x over 2 plus x times, let's see, I'm going to find a common denominator. Notice this guy is going to be x squared over 4, so it would be 4 over 4 minus x squared over 4. Okay, so that would be 4 minus x squared all over 4, like that, plus my constant of integration. And then notice I can take the square root of the denominator, okay, and that's going to give me a 2 down below, so I'm going to have a factor of 1/2 out front, so I get 2 arcsine of x over 2 plus the 1/2 goes out front, so 1/2 times x, I'll just write it as x over 2 times the square root of 4 minus x squared plus my constant of integration. And we're in good shape there. Okay, real good shape. Okay, so you can see how, you know, it's the front end, at least to me, the front end up here is not any big deal. Okay, at least I don't think it is. You guys might, and if you do, that's okay. Okay, but notice how we have to use that power reducing formula down here. Okay, coming right from this guy right here. You got to use it. Okay, and then notice when we get down here, we're going to have to use U substitution to integrate this cosine of 2 theta. Okay, which we do. Okay, and then once we get to here, okay, this is where we have to start doing all that substitution because we got to get the theta out of there. Everything's got to be in terms of x. So once we get, I guess, really kind of like down here, okay, from here all the way to here, it's all about getting rid of the theta, okay, and getting things back in terms of x. Okay, so hopefully you're okay with that. We'll obviously do a couple more of those guys tomorrow and the day after. It might seem tricky right now, but believe me, once you do a handful of them, the process is the same thing over and over again. So it's nowhere near as difficult as it might seem right now. It just takes some practice. Okay, guys, make sure if you haven't gotten your quiz turned in, get that turned in today. Stay safe, and I miss all you guys.